Hi guys, I wanted to make this video on IIR filters within or implementing them on FPGAs because there's not too many videos on how to do this. I want to make a disclaimer that I'm not an expert on this, and I actually just started working on these within the past few months. I'm working on my senior project and in my undergrad, and it has an IIR filter within an FPGA. So I just learned a little bit and thought I'd like to share it with you guys. So let's go over a small outline for the video. It's going to be split up. Well, the videos themselves, there's going to be 3 videos, so they'll be split up into 3 parts. But this video, we're going to go over the prerequisites to know before you need to get into this. We're going to go over a couple different IIR filter structures. We'll go over the biquad, what it is, how and why they are used. I'll show you some MATLAB code that I use to generate the filter coefficients. We'll look at how I coded a simple IIR biquad in Verilog, and then I'll show you the test bench and the test results of the simple IIR filter. And just a little bit of a sneak peek, in parts 2 and 3, I'll write an AxiStream wrapper around the biquad so it can be used with the AxiStream protocol. And then I'm going to cascade multiple biquads in order to create a higher order filter. And why I'll be cascading these will become evident within the next few slides. So prerequisites to know before you get further into the video. It'd be nice if you knew some basic signal processing, so FIR versus IIR filters. In the later sections, I'll be using the impulse response as well as a Fourier transform. So just some basic signal processing theory, or if you've worked with signal processing before in like MATLAB or something, that can definitely help. Knowledge of Verilog is important. That's going to be the language that I'm using. I think the Testbench uses a little bit of system Verilog as well. Familiarity with fixed point math is important. I'll go over it a little bit, but it is important to know if you've implemented an FIR filter on like an embedded system or an FPGA, something like that, you should be okay with moving forward with this video. Access to MATLAB if desired, if you want to run the MATLAB script that I have. And then access to an FPGA simulator of your choice. I'm going to be using AMD Vivado 2024.1. So there's a couple different IIR filter structures. This one right here is going to be the direct form 1 structure. And this one over here is the direct form 2. Whoops. There's more than this. Each structure is going to differentiate itself with the resource utilization within the FPGA, or certain properties of it, as we'll see with the direct form 1, as well as like the delay between output and input, not necessarily the speed of the filter, but the delay from output to input. So we're going to be focusing on the direct form 1 structure, which is this one. Why are we going to do that? Well, here's this quote, and in my GitHub link, I'm going to link the GitHub repository of this project below. You can click on these clickable links right here. These are the sources, and I'll paraphrase this quote, but when we're working with sign numbers in Verilog, they're 2's complement, and if you do like multiplication and addition, sometimes you can get overflow because there's only a fixed width of number that we can store within the FPGA. And that can be complicated. And with other structures, you might need to use like saturation logic or something more advanced. But with the direct form 1 filter, we don't really have to worry about this internal overflow with the 2's complement sign number. So that's why I chose it. It's going to be slightly more simple for me to implement in Verilog. And it's not ideal for a lot of things, but because of this, it's just a little bit easier. So I'm going to also be working with second order sections. And if you haven't heard that term before, second order sections are also going to be known as biquads. This is short for biquadratic. I will go over what this means in the next slide. But basically, it's a second order filter. So you can see here, this is our direct form 1 filter, and it's a second order filter. Why do we use these biquads? This is a quote, so the cascaded biquad design is less sensitive to coefficient quantization than a single high order IIR, particularly for lower cutoff frequencies. So coefficient quantization, what does that mean? Well, when you're working with MATLAB, when you're working with, like, say, a double precision 64-bit quantity or coefficient, you have a lot of room to store that number, its floating point. But when you're in the FPGA, like I was referring to before, you have a limited amount of space to store that number, so you have to round that coefficient. So when you use these biquads and you combine them together, so when you use these second order filters and combine them to create higher order filters, it's going to be less sensitive to that coefficient round off. So that's why we're going to be designing with the biquads. The term biquad is going to be short for biquadratic, and this is a quote. So, and it is a common name for two-pole 2-0 digital filter. So it's a second order filter. The transfer function of the biquad can be defined as that below. Again, there's a link that you can click on, accessed in my GitHub repository. So this is showing the cascading or the combination, and there's multiple ways to combine them, but this is one way. It's just you could cascade the second order sections or the biquads together to create a higher order filter. Note the picture is not direct form 1. So this is going to be our biquad that we create. Before we go back to this, I'd like to show you a little bit of MATLAB code. Okay, so here we are in MATLAB. The first part of this script just closes all, just clears the whole screen out. This is the first important part, and this is where I'm going to generate the test stimulus for the Verilog Testbench. I'm going to generate 1,000 samples coming from, and this is simulated, but it's going to come from a 16-bit unipolar, so it's going to be positive only. So 16-bit unipolar ADC with a sampling frequency of 10 megahertz. So I have my sampling frequency here, my number of samples, and then I have my test waveform that we're going to apply to the filter. So I have a DC offset of 1.65 volts, and this again is simulating the positive nature of the ADC samples. And then have a larger amplitude wave of 50 kilohertz, and then some smaller noise of 2 megahertz. My reference voltage is simulated at 3.3 volts. The precision of the ADC is 16 volts. And what this does is it basically simulates what the ADC is doing, where it's casting it to an integer instead of a floating type. Then it prints it out to this file, and the Verilog code, the Testbench, can actually read this file and output these samples to the unit under test, which we will see later. So I'm going to go ahead and run this, and I'll drag this over, and you can see our test waveform right here. So again, this is 1,000 samples, and it's quite a noisy sinusoid, but we'll see if our filter can take out that high frequency noise. So that's what we're going to do next is design our filter and generate the filter coefficients. So I'm going to do a low pass elliptical filter with a cutoff frequency of 60 kilohertz. And this should eliminate our high frequency noise, and it'll let our 50 kilohertz component pass as well as the DC component. So you can see I got my cutoff frequency there and my elliptical filter generating the B and A coefficients. Let's take a look now at the frequency response of the filter as well as the Z-plane to make sure it's stable. So you can see both of the poles right here are inside the unit circle, so we're stable on our filter there, and you can see our frequency response here. I'm going to exit both of these out. Now, this is going to take a second to explain, but the SOS refers to the second order section or the biquad, and we have a second order filter but I did want to show this a little bit. You can use this TF to SOS to take the transfer function from these and generate an SOS matrix with G referring to the actual gain of that SOS section. So I'm going to enter that, and you can see down in the command window right here, I have all of my coefficients and the overall gain of that that section. So this gain, it normalizes or I think this is what it does. You can correct me if I'm wrong in the comments below, but I think it normalizes this B0 coefficient to 1, and so that's what that gain represents. If you looked at let's see here. If you looked at it before, the B0 coefficient would actually have been this gain. It's okay to embed this in the direct form 1 filter structure. So I'm going to show you just a brief glimpse of the Verilog code and show you what I'm talking about. So right up here, you can see I have the SOS matrix, and I also have the gain. If you click on the source up here in the description of the code, it's going to show you that it's okay to multiply the gain by the coefficients for the B coefficients. That's called embedding the gain, and this is okay for direct form 1. MATLAB doesn't recommend this for direct form 2. I'm not sure how other structures go, so again, we're not going to need this SOS matrix, but I did want to show that we're going to be using that in the future parts. Okay, so next we're going to go over how do we convert these coefficients to fixed point. Well, we got to convert them from floating point to fixed point, and in the Verilog code, you can see my multiplier, or my coefficient width is going to be 16 bits. So 15 down to 0 is 16 bits. I'm going to go back to my MATLAB, and I have a 16-bit sine multiplier width. So I'm going to need 1 bit for the sine. So it's a 2's complement, so 0 is positive, 1 is negative. I'm also going to need the bit next to that for the 1's place. You can see in our coefficient matrix down here, the maximum of the digit in the 1's place is just going to be 1. It's either 0 or 1. So I only need 1 bit to represent that. So out of the 16 bits, that's going to leave us 14 bits for this fractional part right here. What we're going to do is multiply everything by those 14 bits, then round it or truncate it. That's what the fix does. And then we get an integer number. And the integer number is much easier to multiply within the FPGA or your embedded system. So I'm going to go ahead and do that and show us. This down here is going to show us the fixed point A coefficients and the fixed point B coefficients, again, both in integer form. So you can copy these into your Verilog code, but before you do that, when we round them and multiply them, we want to check the stability of them after. So that's what the last part of this script does right here. So I'm going to run that small part and drag this over. And so they got rounded off a little bit. I think they moved further away from the unit circle, but they're still inside and we're still good to go. So the filter's still stable. We're all good to go. Let's move on to the Verilog code. Okay, so here's our biquad that we're going to build with the Verilog code. I have 3 ports. I have the clock, I have the D in and the D out, the data in and the data out. Both of these ports are signed with a width of 16 bits. Below that, I have my filter coefficients stored as signed registers. And this is what we just did in the MATLAB code. So you can see I just copied those over. A1 fixed, A2 fixed, B0, B1, and B2. Fixed represents that they're in fixed point notation. You'll notice we don't have an A0 coefficient. That's because the A0 is actually always 1, and so we don't need to multiply by anything because anything times 1 is just itself. I have an input register, and I have an output register. Then I have these delay registers. So these in our biquad diagram, these Z to the -1, those are going to be delay elements. So you can see here, this top one is going to be R_X_Z1, and the bottom is R_X_Z2. The R in front of this refers to the fact that it's a register. Those are 16 bits because those are going to be holding input samples as well as the feedback samples from the output. Below that, I have multiplication wires. These are going to store our products. These are not registers, these are wires, but again, signed. And you'll notice the width, so 32 bits, again, to be able to hold the product of two 16-bit numbers. We have a 16-bit input from our registers and a 16-bit signed coefficient. So our product needs to be 32 bits wide. I also have this wire here, which is 32 bits wide, which is the sum wire. That's this blue portion right here. That's going to cover all the addition or the summation in our filter. Down here I have the only sequential logic block in this code. So at every positive clock edge, and all this is going to execute simultaneously, but I'm going to register the input. Then these are going to shift samples down into the delay elements. This line right here is interesting. So when we multiplied all our coefficients up here by our scale factor, which again was 2 to the 14th, so 14 bits for that fractional component, what we need to do on the output is scale it back down. This is done by an arithmetic left shift. So that's the three, I'm blanking on what these symbols are called, but an arithmetic left shift is going to keep the sign, and then since it's a power of 2, the left shift is going to act like a division. So it's dividing by the same 2 to the 14th value that the coefficients were multiplied by. And again, we're dividing that sum wire, so it's going to be right here that we're dividing to get back to that original width. Again, down here, we're going to be shifting samples from the feedback path into the delay registers. Right here, I do the multiplication. This is combinational logic. This is not clocked logic, which we'll discuss at the end of the video. But just important thing to note is these two negative coefficients, which are, you can see in the biquad diagram, those are in fact supposed to be negative. The second to last thing is this sum wire, and it's just a summation of all of the products. You can see this blue here, which I had already mentioned. And then I assign the D-out port to one of the registers. That's the filter. It's pretty simple, especially when you have a diagram to go by. One of the things that helps me with Verilog is making a diagram, because it's not like software where things go line by line. You really are writing hardware. So that's how I came about this, and it's one of the reasons why I chose the direct form one. It has that, you don't really have to worry about overflow as much, and this wire, the summation in the middle, just made sense to me. So yeah, I'm going to go over to the test bench here and maximize that. Just explain the test bench a little bit. This is an important note. So when you're using the test bench to read the TXT file with the samples, the .txt file, which was generated in MATLAB that holds all the samples, you have to place the TXT file in this directory in order for Vivado to find it. So I'm going to pull up mine and show you where it goes. So I'm in my project directory, and I'm going to go to the project directory.sim or the project name.sim, sim1, behave, xsim. And you can see I have my teststimulus.txt file right here. It's in that directory, and that's where it has to be for Vivado to find it in order for the test bench to be able to read it. So I'm going to go back to the test bench, and again, I have 3 ports for my unit under test. 10 megahertz clock. So the clock frequency is going to be the same as our sampling frequency for this. These integers here, a couple are for file read, and then some are for one of this initial block. Number of samples, I have 1,000 samples that I generated. This is a two-dimensional register, assigned register that's going to store all of the samples. I then instantiate my unit under test and start my initial block. I initialize the clock to 0 and the data in to 0. I'm going to open the file that we generated in MATLAB with all the test samples. I'm going to fill up that two-dimensional register with all of those samples. I'm going to close the file, and then this is a short repeat block, so repeat for the number of samples. I'm going to wait for the positive edge of the clock, and then I'm going to output the new sample. So again, it's just chugging out these samples as they go through. We're going to wait a small amount of time, and then we're going to finish. Okay, so I'm in Vivado, and I created a new project, and I added my sources in, and I did make sure that sample, this test stimulus was in the correct spot that I showed you. On the waveform viewer, I have three signals. I have my clock, I have the test stimulus that we're applying, and I have the data output of our unit under test. What I did is you can go to waveform style and hit the analog to view it in an analog form. And then I also made sure that I was using the signed decimal version or setting for this. So I'm going to go ahead and run it for a little bit, and we will see what happens. So you can see here, quite noisy input sinusoid. And then on the output, no more noise. So our filter does in fact work, works pretty well. And we were able to filter out that high frequency noise while keeping the same low frequency component. There's a couple issues with this, and that's what I'm going to discuss next, and then we'll move on to the other parts of the video. Okay, so what are the potential issues with this code that we just built? It's simple and easy to understand, and it does work, but there are a couple issues with it. The first one is that there's no standard interface. There's no AXI interface or similar. Each sample is going to be loaded on the system clock edge. So what if you needed to have a ADC that was running significantly slower than your system clock? You could run into issues with this. And then as well as interfacing to other sensors, let's say you had in your SoC design some things that were outputting like samples on an AXI stream, you wouldn't be able to interface with that. Can we increase the multiplier width for less coefficient rounding and less error? Can we do that? Yes, we can absolutely do that. We'll get into that in the next video. There's no parameterization in this code, so it'd be hard to rewrite for different sizes, like input sizes or output sizes, or again, that increasing the multiplier width. One of the big issues is the poor pipelining of it. So the maximum speed that this device can, or this code can run at is a little above 50 megahertz. Or it's somewhere in between 50 and 100 megahertz. It passes timing at 50 megahertz and it fails timing at 100 megahertz. So just keep that in mind. That's due to, while the multiplication is sequential, the addition is not, and it's a poor use of the DSP tile. What I'm using these IIR filters for is an EKG signal, and the sampling frequency is at 500 hertz. So I'm not too worried about, I don't need the filter to be running at higher than 50 megahertz. So I'm okay there. You might not be, and you might want to better pipeline it. But yeah, thanks for watching this. Please click on the next section of the video where I create an AXI stream wrapper around this and do a little bit more testing.